What is the biggest thing in the universe? It's a question that seems simple until you try to answer it. Maybe you picture a giant star, or a swirling galaxy, or even a monstrous black hole devouring everything in its reach. But these, vast though they are just points of light in the great darkness of space. For decades, astronomers believed the largest things were superclusters, titanic webs of galaxies stretching across hundreds of millions of light years. Our own Milky Way is just a tiny thread in one called Laniakea. But even these aren't the true giants, because the largest structures in the universe are made of nothing. Cosmic voids, immense regions of almost perfect emptiness, stretch across billions of light years, dwarfing everything around them. They don't shine, they don't burn, but they shape the very skeleton of the cosmos. To understand the universe, we must first understand the void. In the year 1985, a team of astronomers led by John Hutra at the Harvard-Smithsonian Center for Astrophysics was completing one of the most ambitious galaxy surveys of the time. Using telescopes to scan the skies in the direction of the constellation Coma Berenices, they were mapping the positions of thousands upon thousands of galaxies. Each point of light they recorded was not a star, but an entire galaxy, an island of hundreds of billions of stars, each one tens of thousands of light years across. As the team began to compile and visualize their data, something strange emerged. The galaxies were not scattered randomly. Instead, they began to cluster, to form patterns. And then, out of the darkness, a shape slowly came into focus. A figure stretching across hundreds of millions of light years. It looked unmistakably human. A long torso, arms reaching out, legs bent in motion. It resembled a simple stickman, the kind drawn by a child. But this was no myth, no illusion. It was a map, and it was telling a story. This stickman, dancing silently across cosmic distances, was not a single object, but a vast structure. A network of galaxies connected by gravity into a larger whole. It was one of the first real glimpses humanity ever had of a supercluster, a colossal web of galactic matter laced across the sky. The universe, it seemed, was not a random sea of galaxies. It was structured, organized, and what this structure revealed was only the beginning of a far greater mystery. One that would turn our understanding of the cosmos inside out. When we look into the night sky, we see stars. Through telescopes, we see galaxies, massive spirals and glowing ellipses, each one home to hundreds of billions of stars. But galaxies do not exist in isolation. They gather together into groups, and those groups gather into clusters, dense cities of galaxies bound together by gravity. For much of the 20th century, astronomers believed that galaxy clusters were the largest organized structures in the cosmos. But they were wrong. In time, a deeper truth was revealed. Galaxy clusters, as massive as they are only parts of something even more immense. Clusters connect to each other through long filaments, cosmic strands composed of galaxies, gas, and dark matter. These filaments, in turn, form vast networks that stretch across hundreds of millions of light-years. These are the superclusters, the true giants of the visible universe. They are not bound in the same way as clusters are, but their scale is so enormous that gravity still weaves them into coherent forms. Superclusters are among the largest known formations of matter in the cosmos. A single supercluster can contain tens of thousands, or even hundreds of thousands, of galaxies. The smallest of them are several hundred million light-years across. The largest span more than 10 billion light-years, distances so vast they defy ordinary comprehension. And yet, they are not rare. Current estimates suggest that there may be as many as 10 million superclusters within the observable universe. Our own galaxy, the Milky Way, is part of a relatively small group of galaxies known, quite unceremoniously, as the local group. This group orbits within a larger structure, the Virgo cluster. The Virgo cluster is itself only a small branch of a much greater supercluster, a sprawling structure named Laniakea. The name comes from the Hawaiian language and means immense heaven, a title that could not be more appropriate. Laniakea stretches over 500 million light-years and contains over 100,000 galaxies. Superclusters like Laniakea are not spherical. They do not resemble galactic globes floating in space. Instead, they are tangled, branching networks. Filaments twist and thread like vines through the void, connecting galaxy clusters at intersections and stringing galaxies like beads along invisible strands of dark matter. At some locations, these filaments cross, and where they do, immense clusters form, gravitational nexuses, where hundreds or even thousands of galaxies collide and interact over billions of years. The names of superclusters often reflect the constellations through which they are observed: the Coma supercluster, the Hydra Centaurus, the Perseus Pisces. Others, more distant or less understood, are catalogued by numbers and designations, but some receive more imaginative titles. One of the most massive known superclusters, discovered in 2022, was named King Ghidorah, after the three-headed nemesis of Godzilla. These names are whimsical, but the structures they represent are anything but. Their scale is beyond comprehension, and their mass rivals anything else in the cosmos. A typical supercluster can contain more than 10 million billion times the mass of our Sun. The galaxies inside orbit, twist, and fall toward one another over cosmic timescales. The entire structure is shaped not only by normal matter, but by dark matter, an invisible scaffolding that defines the gravitational skeleton of the universe. And yet, despite their size, superclusters are not static. They are dynamic, evolving. Most are not gravitationally bound in their entirety, and over time, the accelerating expansion of the universe may pull them apart. Even with their astonishing size and complexity, superclusters are not evenly distributed. They are woven into a grand structure, the cosmic web. This web, spanning the observable universe, is composed of filaments and nodes, of superclusters and clusters, all connected across space. The cosmic web is not uniform. It is full of gaps and voids, walls and strands. It is a living map of gravitational evolution, a frozen echo of the universe's earliest moments. But as we shall see, for all the grandeur of superclusters, they are not the final word in cosmic scale. Something even larger waits in the spaces between. When astronomers first mapped the universe in 3 dimensions, they expected to find a relatively even sea of galaxies. After all, cosmological theory had long held that the universe, on large enough scales, should be homogeneous, essentially the same everywhere. But what they found told a very different story. Rather than uniformity, they saw patterns. Galaxies were not scattered randomly like grains of sand. Instead, they clustered along long, thin strands, intersecting at dense nodes. And in between those threads, there was nothing. These dark regions were not small gaps or empty patches. They were vast expanses, some hundreds of millions, even billions of light years across, where almost no galaxies could be found. These were the voids, the shadows in the cosmic web. And while they were difficult to detect directly, their presence was unmistakable. The galaxies seemed to trace the edges of something larger, something hidden. The voids were not just blank space. They were shaping the very architecture of the universe. The first discovery of a void came not from theory, but from perseverance. In the late 1970s, astronomers Brent Tully and Richard Fisher were surveying galaxy positions when they found a large region in the sky that contained almost no galaxies at all. This region, eventually named the Bootes Void, appeared to be a hole in the cosmos, a space where, against all expectations, nothing existed. Initially, the idea was met with skepticism. Many believed it was an error, a flaw in the data. But more observations confirmed the truth. The Bootes Void was not alone. Over the following decades, astronomers discovered more and more of these cosmic voids. As galaxy surveys grew more comprehensive, it became clear that voids were everywhere. In fact, most of the universe is void. Galaxies and clusters make up only a tiny fraction of the universe's volume. Nearly all of space, by far the majority, is made of emptiness. The cosmic web, as majestic as it appears, is only a thin lattice stretched across an ocean of darkness. And yet, the voids are not truly empty. Though nearly devoid of galaxies, they still contain a whisper of matter. An atom here, a stray neutrino there. The density within a void is often less than 20% of the cosmic average. In human terms, this would be like walking across a desert where there is only 1 grain of sand per cubic meter. Within the heart of a void, one could travel for millions of light years without encountering a single galaxy. These are the loneliest places in the universe. It is not only normal matter that is absent in the voids. Dark matter, the invisible substance that dominates the mass of galaxies and clusters, is also missing. Simulations show that the filaments and walls of the cosmic web are rich in dark matter, but the voids are nearly empty. That is why galaxies do not form there. There is nothing for gravity to work with. The bright galaxies we see are merely lighthouses on the edge of a much darker and deeper structure, one defined not by presence, but by absence. Even more surprisingly, voids themselves have structure. Recent simulations have revealed that voids can contain subvoids and even smaller nested voids within them. In some places, faint galaxies within the voids arrange themselves into delicate filaments, tiny echoes of the larger cosmic web outside. This fractal-like hierarchy means that the emptiness of space is not simply a featureless abyss, but a layered system, shaped by the same forces that built the galaxies and clusters we observe. The voids, once dismissed as curiosities or mistakes, have now become central to our understanding of the cosmos. They are not merely gaps between structures. They define those structures. The clusters, the filaments, the superclusters, all of them are suspended like threadwork on the edge of the abyss. To understand the universe, it is no longer enough to study the matter. We must also study the voids, the shadows that give shape to the light. For in those shadows lies a deeper truth, one that stretches far beyond the galaxies we know. In the earliest days of void discovery, the astronomical community did not react with wonder, but with resistance. The idea that vast swaths of the universe could be empty challenged the prevailing view of cosmology. Many astronomers argued that the voids were illusions, flukes in data collection, or simple misunderstandings of how galaxies were distributed. After all, it was widely believed that the universe, when viewed on large enough scales, should appear roughly the same in all directions, without such immense irregularities. This skepticism was not born from arrogance, but from tradition. For decades, cosmology had operated under the assumption of homogeneity, that the cosmos was smooth and balanced when viewed from afar. Clusters and superclusters were accepted, but voids, huge gaps in the distribution of galaxies, were seen as statistical noise. Observers in Europe and America were particularly reluctant to accept them, clinging to models that could not explain their existence. But far from the Western scientific establishment, another group of researchers was seeing something different. In the Soviet Union, a radically different picture of the universe was beginning to emerge. Led by the brilliant theorist Yakov Zeldovich, Soviet cosmologists proposed a model of cosmic evolution that allowed for both density and emptiness. According to Zeldovich, matter in the early universe would collapse along sheets and filaments, creating clusters and galaxies, but leaving behind vast regions of low density. In this view, voids were not mistakes. They were inevitable. They were the natural consequence of the universe's growth. While Western scientists dismissed voids, Soviet researchers began searching for them deliberately. In the late 1970s and early 1980s, astronomers in Estonia and Russia published surveys that supported the existence of large-scale voids. Although these surveys were not always as refined as their Western counterparts, they revealed holes, enormous regions with few, if any, galaxies. To these scientists, the universe was not a uniform ocean of stars. It was a fractured web, shaped as much by absence as by presence. The tide began to turn in the early 1980s. In a survey directed by American astronomer Robert Kirshner, researchers studied a different region of the sky and found the same startling result: a void, vast and undeniable. It became known as the Buta's Void, and its discovery marked a turning point. This was no isolated case, no mistake of measurement. There were now multiple independent confirmations of cosmic voids from different teams in different parts of the world. The pattern could no longer be ignored. With the weight of evidence mounting, cosmologists were forced to reconsider their assumptions. The old models of smooth, uniform distribution gave way to a new understanding. The universe was structured, and that structure included the existence of voids. These were not holes between galaxies. They were the framework within which galaxies formed. What once seemed like blemishes were, in fact, features, critical pieces of the cosmic puzzle. In accepting the voids, science took a leap toward a more accurate map of the universe. The discovery of voids marked the beginning of a new era in cosmology. No longer could astronomers rely solely on light to define the cosmos. Now, darkness mattered too. The empty spaces between galaxies were no longer empty of meaning. They shaped the cosmic web, defined its contours, and revealed a deeper, more intricate truth: that the universe is not simply a collection of matter scattered through space. It is a story of contrast, of tension between light and darkness, presence and absence. And the voids were here to stay. Once astronomers accepted the existence of voids, a much grander question emerged. What does the universe really look like? Not just as dots of light scattered across the sky, but as a structure, a three-dimensional map of everything. To answer this, scientists needed not only better telescopes, but also a new way to think. The universe, as it turns out, is not a featureless expanse. It is a web, an intricate, interconnected structure known as the cosmic web, the largest known pattern in the cosmos. The first hints of this web came from galaxy redshift surveys. These surveys measured how much the light from a galaxy had been stretched due to the expansion of the universe, allowing scientists to calculate how far away each galaxy is. When these data were plotted, galaxies appeared not in random positions, but along long threads and flattened walls, intersecting at dense clusters. Between them were immense gaps, the voids, further reinforcing the idea that matter in the universe follows a very specific, organized pattern. As survey techniques improved, a clearer picture began to form. Astronomers saw that galaxies trace out thin filaments, like strands of silk, stretching across hundreds of millions of light years. These filaments connect to one another at nodes, regions where massive galaxy clusters reside. Between the filaments lie vast voids, cold and quiet, largely empty of galaxies or dark matter. What once looked like chaos now revealed the elegant architecture of gravity acting over billions of years. The structure was not entirely smooth. It resembled foam or a sponge, with dense walls and filaments forming boundaries around the empty regions. Some of these walls span over 1 billion light-years. The entire observable universe, nearly 95 billion light-years in diameter, is filled with these interconnected superclusters, clusters, filaments, and voids. It is a network of unimaginable scale, stitched together by gravity, time, and the expansion of space itself. This is the true skeleton of the cosmos. Perhaps the most important surveys in this mapping effort were the Sloan Digital Sky Survey and the 2-degree Field Galaxy Redshift Survey. These projects mapped hundreds of thousands of galaxies, creating a 3-dimensional view of the local universe. When viewed from a distance, the distribution resembled neural networks or root systems, organic and patterned. The map revealed that even our own galaxy is just one small point on a vast thread, resting on the edge of a void, pulled gently toward the center of a greater mass. To visualize the cosmic web, scientists began to rely on supercomputers and simulations. These simulations used the laws of gravity, thermodynamics, and dark matter physics to recreate how structure in the universe formed over billions of years. By inputting the conditions of the early universe, researchers could watch virtual galaxies emerge, cluster, and settle into the same filamentary structures we observe in the real universe. These digital models match the real-world surveys with astonishing accuracy. From these simulations, a new understanding took shape. The web is not made only of visible matter. In fact, most of it is composed of dark matter, an invisible, unknown form of mass that interacts through gravity but emits no light. Galaxies form where dark matter is densest, lighting up only the brightest knots in an otherwise invisible net. Between these knots, the web stretches thin, almost transparent, sculpting the distribution of everything we can see. It is not the galaxies that define the universe, but the unseen network that holds them. And so, by mapping the positions of galaxies, tracing the filaments, and studying the yawning voids in between, astronomers have built a new map of the universe, one that reveals its hidden form. The cosmic web is not just a pattern of galaxies, it is the fingerprint of creation, a memory of how gravity shaped the cosmos from the tiniest fluctuations in the early universe. In this map, we find not only our location, but our story. We are not adrift in a random sea. We are perched on a single thread of a web that stretches beyond imagination. At first glance, a void seems like a blank space, an empty region devoid of galaxies, stars, and matter. But as astronomers began to peer deeper into these vast expanses, they discovered something unexpected. The voids are not uniform. They are not featureless chasms. Instead, they contain delicate internal structure, whispers of galaxies, faint filaments of gas, and small pockets of clustering. Like the larger universe they inhabit, voids are shaped by gravity. And gravity, it seems, never stops drawing patterns, even in the silence. Within the largest voids, astronomers began to detect smaller voids nested inside. These subvoids, in turn, contain even smaller gaps, surrounded by dim strands of matter. This nesting continues on multiple scales, forming what scientists now call a fractal structure, a repeating pattern that persists regardless of how far in or out one looks. From the largest supervoids to the tiniest hollows in the distribution of matter, the same geometry reappears. The structure of emptiness is, in fact, not empty at all. This realization changed how cosmologists define voids. Rather than viewing them as single, isolated bubbles, they are now seen as valleys in a complex cosmic landscape. To understand this terrain, scientists borrowed a technique from Earth science, the watershed algorithm. On our planet, a watershed is the region where all rainfall flows toward a single point, divided by ridges and mountaintops. In space, voids are the basins, and the high-density filaments and clusters are the ridgelines. The matter flows away from the voids and toward the peaks. Using this method, cosmologists were able to trace the boundaries of thousands of voids in the nearby universe. The Sloan Digital Sky Survey and other large-scale observations provided the raw data, and supercomputers helped identify and map the shapes and depths of each void. What emerged was not chaos, but organization. Voids appeared to arrange themselves into a larger hierarchy, with the largest voids encompassing many smaller ones, each defined not by mass, but by the absence of it. This hierarchy is not merely a mathematical curiosity. It holds deep implications for how structure forms in the universe. As galaxies form along filaments, material is pulled away from the voids. The richer the filaments become, the more the voids are depleted. But because of their fractal nature, this process happens at every scale. Tiny filaments pull matter from microvoids, just as massive structures shape the largest cosmic gaps. In the end, the structure of nothingness mirrors the structure of everything. The galaxies within voids are also peculiar. They tend to be smaller, dimmer, and redder than those found in clusters. These galaxies form in relative isolation, with fewer collisions or interactions to trigger star formation. In some voids, they form faint miniature webs of their own, a shadow of the larger cosmic web outside. These miniature structures are fragile, almost ghost-like, yet they reveal how gravity still molds matter, even in the universe's most desolate domains. What emerges from all this is a humbling insight. The absence of matter is not the absence of form. The universe draws structure not only from abundance, but also from scarcity. The voids are not silent voids of meaning. They are recursive, ordered, and deeply connected to the processes that govern the entire cosmos. In their vast, layered emptiness, they reflect a strange truth, that even in the quietest places in the universe, there is still a pattern waiting to be understood. As astronomers mapped more voids across the sky, a new mystery emerged, one not from the present, but from the ancient past. When we observe the cosmos in microwave light, we are looking at the afterglow of the Big Bang. This radiation, known as the cosmic microwave background, is the oldest light in the universe. It was released when the universe was only a few 100,000 years old, and it reveals subtle variations in temperature that reflect the earliest seeds of structure. Among these fluctuations, one stood out. It became known simply as the cold spot. Compared to its surroundings, this region of the sky appeared unusually cold, colder than predicted by standard cosmological models. It was not just its temperature that puzzled scientists, but its size. The cold spot spans hundreds of millions of light years across the sky, far larger than most temperature fluctuations in the cosmic microwave background. Its statistical significance was troubling. According to accepted theory, such a large cold region should not exist. Many explanations were proposed. Some considered it an error in the data or a rare coincidence. Others suggested new physics, a sign of interactions between universes, or a tear in the cosmic fabric itself. But one theory stood out for its elegance. Perhaps the cold spot is not a feature of the early universe at all. Perhaps it is a shadow cast by something vast that lies between us and the ancient light. That something, scientists proposed, could be a supervoid. A supervoid is not just an ordinary void on a larger scale. It is a cosmic depression of such vast size and depth that it affects the light traveling through it. When photons from the cosmic microwave background pass through such a void, they lose energy. This happens because the void expands while the light is passing through it, stretching space-time and altering the energy of the photons. As a result, the light exits the void cooler than when it entered, creating a cold imprint on the sky. In 2014, a team of astronomers discovered a supervoid in the direction of the cold spot. It was named the Eridanus supervoid, and it appeared to stretch over 1 billion light-years in diameter. Though it alone could not fully explain the cold spot's properties, it lent strong support to the idea that supervoids can influence cosmic microwave background radiation. It was not the final answer, but it was a powerful clue, a reminder that the dark places in the universe shape even the light that passes through them. The Eridanus void is not alone. Other supervoids have been discovered, including the so-called Kaiva Vash void and the Giant Void, one of the largest empty regions known. But the most controversial of them all is the proposed KBC void, named after its discoverers, Keenan, Barger, and Cowie. This enormous depression, if it exists, could stretch nearly 3 billion light-years across and might even encompass our own Milky Way galaxy. Its existence would have profound implications. The KBC void was proposed not to explain the cold spot, but to address a different cosmic puzzle: the tension between measurements of the Hubble constant. When astronomers measure the expansion rate of the universe using nearby galaxies and supernovae, they get a different value than when they calculate it from the cosmic microwave background. The KBC void, with its lower density, could cause local measurements to differ from global ones. In this way, a single massive void could shift our entire understanding of cosmic expansion. Yet, the KBC void remains unconfirmed. Its size is so immense that independent verification is difficult. Some cosmologists argue that voids of this scale break our models of structure formation, that they are too large to exist within a universe governed by known physics. Others believe these supervoids are rare, but not impossible. As data improves and surveys deepen, we may one day confirm or refute their existence. Until then, they remain both an opportunity and a threat, a chance to glimpse something new, or a challenge to everything we think we understand. The discovery of voids, and especially supervoids, has transformed our understanding of the universe's large-scale structure. But it has also presented a troubling possibility, one that cuts to the very heart of modern cosmology. Could these immense regions of emptiness be too large to exist? Could they represent a breakdown in our current models of how the universe forms and evolves? For some researchers, this is not just a curious anomaly. It is a genuine threat to the foundations of cosmic theory. To understand why, we must consider the idea of homogeneity. Cosmology rests on the principle that, when viewed on a large enough scale, the universe is the same everywhere. It does not matter where you are or which direction you look. Over hundreds of millions of light years, the distribution of matter should be statistically uniform. This concept is essential. It is built into the equations of general relativity and underlies all of our models for cosmic expansion, dark matter, and dark energy. This assumption has been remarkably successful. It has allowed scientists to simulate the formation of galaxies, predict the distribution of clusters, and match observations across decades of data. But supervoids, by their very nature, push against the limits of this principle. If a single void spans over 1 billion light-years, it challenges the notion that any region of space can be considered representative of the whole. It suggests that our patch of the universe may not be as average as we once believed. This is more than just a statistical nuisance. If the largest voids are real, and some, like the proposed KBC void, may encompass a significant portion of the local universe, then many of our measurements could be skewed. Observations of galaxy velocity, brightness, and even the Hubble constant might be biased by the gravitational effects of such massive underdensities. What we think of as universal laws might in fact be local artifacts, shaped by where we happen to exist inside the cosmic web. Some cosmologists have proposed that the presence of these supervoids might require new physics. Perhaps an unknown form of matter or a fifth fundamental force is at play, subtly influencing how matter clusters and empties across the universe. Others have turned to radical alternatives, including modifications to general relativity, or even models that allow for different expansion rates in different regions of the cosmos. These ideas are not widely accepted, but they show just how serious the implications of supervoids might be. Still, not everyone agrees that the threat is real. There is a counterargument grounded in probability. In a universe as vast as ours, rare events are expected. A supervoid might be statistically improbable, but not impossible. With enough space, even the most unlikely features can appear. In this view, the largest voids do not break the rules of cosmology. They are simply extreme examples of them. The universe is large enough to produce its own exceptions. As more data are gathered from deep sky surveys, some of these questions may find answers. Telescopes like the Vera C. Rubin Observatory and the Nancy Grace Roman Space Telescope will map the positions of billions of galaxies, offering a more precise measurement of cosmic structure than ever before. These surveys may help us determine whether supervoids are statistical flukes, genuine anomalies, or signs of something more profound. Until then, they remain unresolved puzzles at the edge of science. What is clear is this: the voids are growing. They are not static scars in the universe's fabric. They are evolving, expanding, and deepening as time marches on. If they continue unchecked, they will one day dominate the large-scale structure of the cosmos. Whether this growth is consistent with current theory or demands a new one remains to be seen. But in their silent, sprawling presence, the voids challenge us to look again at what we thought we understood, and to ask whether the universe is truly as simple as it once seemed. By the end of the 20th century, astronomers had uncovered something deeply unsettling about the universe. Observations of distant supernovae revealed that galaxies were not only moving apart, they were accelerating away from each other. The expansion of the universe was speeding up. This was not expected. According to gravity, the universe should be slowing down over time, not rushing apart faster and faster. To explain this, scientists introduced a mysterious new force: dark energy. Dark energy is not like any energy we know. It does not clump, it does not glow, and it cannot be touched or seen. It is thought to be a property of space itself, an inherent energy that fills the vacuum. Even when every particle of matter and light is removed, dark energy remains. It behaves like a kind of anti-gravity, pushing things apart rather than pulling them together. And remarkably, it is not rare. Dark energy is believed to make up nearly 3/4 of the total energy content of the universe. But dark energy does not act equally everywhere. In regions where matter is dense, such as galaxies and clusters, its effects are overwhelmed by gravity. These places are anchored, held together by their own mass. But in the vast empty voids between structures, gravity is weak. There, dark energy dominates. It pushes outward in all directions, stretching space itself, thinning the boundaries between filaments, and hollowing out the universe's most isolated regions. The voids are not just shaped by dark energy, they are driven by it. In this sense, cosmic voids are laboratories for dark energy. They are the places where its effects are most visible. As voids grow, they squeeze the matter around them. Filaments become thinner, galaxy groups drift apart, and the gravitational bridges that once tied structures together begin to break. The process is slow but relentless. With every passing billion years, the web of galaxies becomes more frayed. The architecture of the cosmos is being unstitched, not by violence, but by gentle, inexorable pressure. This process is not just a prediction, it is something we are already observing. When scientists measure the expansion of space in voids compared to that in denser regions, they find differences. Voids appear to be expanding more rapidly than the universe as a whole. They are, in effect, growing faster. This behavior supports the idea that dark energy is not only real, but actively reshaping the universe. The emptier a region becomes, the more dark energy fills it. The more dark energy it contains, the faster it expands. And this cycle feeds itself. As voids expand, they gather more dark energy. That dark energy, in turn, accelerates their growth. Over cosmic time, this means that voids do not just exist alongside matter, they will eventually overwhelm it. The clusters and filaments that define the cosmic web will be pulled apart until they are isolated islands in a sea of nothingness. In the far future, the universe will not be a web of light, but a collection of dim, cold remnants drifting in an ever-expanding abyss. This fate, often called the Dark Era, is one of the possible ends of the universe. Stars will burn out, galaxies will fade, even black holes will evaporate, but the voids will remain, vast and unchanging, filled with nothing but the pressure of dark energy. In a strange twist, the emptiest places in the universe will be the last to persist. They will outlive the stars, the galaxies, and the filaments. The final echo of the cosmos will be silence, carried outward by the force that now drives its expansion. But until that distant epoch, the voids still have a role to play. Because they are so sensitive to dark energy, they offer one of our best chances to understand it. By studying how voids grow, how they shape galaxy formation, and how they differ from predictions, scientists can refine their models of dark energy's nature. In this way, the voids are not just symbols of cosmic decay, they are tools for discovery. Through them, we may yet unlock the deepest secrets of space, time, and the future of everything. In a universe filled with stars, galaxies, and intricate cosmic webs, it is tempting to think that complexity lies in what we can see. The luminous structures, the rotating galaxies, the swirling clusters, these appear to be the true engines of cosmology. But in truth, they are noisy, they are messy, they are difficult to untangle. The galaxies, for all their brilliance, are built from chaos, collisions, radiation, magnetic fields, and bursts of star formation. Each one is a puzzle of processes layered over billions of years. If we want to understand the origin and fate of the cosmos, we must find clarity. We must look for simplicity. And the voids, ironically, offer that. These vast regions, once thought to be lifeless and unimportant, now reveal themselves as the most pristine environments in the universe. There is no turbulence, no crowding of matter, no confusing feedback loops. In their silence, the voids preserve the early conditions of the cosmos, stretched and scaled, but not yet disturbed. Cosmologists now treat voids not as empty gaps, but as cosmic fossils. Because they are so empty, they have changed very little over time. Unlike galaxies and clusters, which have evolved through countless interactions, voids have simply expanded. They have grown quieter. Their structure is shaped more by geometry than by chaos. This makes them ideal for reverse engineering the universe, working backward from what we see today to infer the state of the early cosmos. The simplicity of voids also makes them ideal probes of dark energy and dark matter. In galaxies, dark energy is overwhelmed by gravity. In clusters, the density of matter clouds our ability to isolate subtle effects. But in voids, the influence of dark energy is pure. There is no confusion, no interference. The signal is clean. When cosmologists build simulations, they often turn to voids as calibration zones, places where they can test theories against near-perfect silence and structure. Even more remarkably, voids may contain their own internal architecture. Studies suggest that galaxies within voids are not distributed randomly. Instead, they follow faint, ghost-like filaments, miniature versions of the cosmic web. These internal filaments show signs of structure within structure, hinting at a fractal nature that may extend far deeper than we can observe. In this way, the voids mirror the universe itself, complex in form, but simple in origin. And yet, this simplicity is not boring. It is beautiful. The voids are not nothing. They are the canvas on which everything else is drawn. Without emptiness, structure would have no shape. Without silence, music would have no rhythm. The galaxies shine brighter because they are surrounded by dark. The universe has meaning not just because of what exists, but because of what does not. The voids frame the story of creation. As our telescopes become more powerful and our maps more detailed, we will no doubt find new complexities in the universe. But the voids will remain as they are, still, expanding, and elegantly simple. They are not just vast, they are profound. They remind us that the cosmos is not merely a celebration of presence, but a meditation on absence. They are the quiet echo of the Big Bang, carried outward through space and time. And so, in the search for understanding, we must learn not only to look at the light, but to listen to the silence. The voids may appear empty, but they are full of answers. They speak a different language, one of patience, expansion, and equilibrium. In their quiet simplicity, they reveal what complexity cannot: the hidden structure of the universe, the forces that shape it, and the destiny that awaits us all. For as long as humans have gazed into the sky, we have sought answers in the places that shine. The stars became our calendars, the planets, our myths, the galaxies, our frontiers. It is a natural impulse to be drawn to light, to the visible, to the brilliant beacons scattered across the black canvas of the cosmos. And for centuries, this impulse served us well. It led to great discoveries, from the structure of our solar system to the expansion of the universe itself. But now, as our tools and theories have grown more refined, we have begun to realize something unexpected: that the true shape of the universe is not defined by what is there, but by what is not. The cosmic voids, once dismissed as meaningless gaps between galaxies, are now recognized as the largest and most fundamental structures in the universe. They stretch across billions of light years, encompassing volumes so vast that entire clusters and superclusters appear as threads on their edges. These voids are not passive. They are dynamic, growing, and evolving. They expand faster than the rest of the universe, driven by dark energy. They shape the filaments that stretch between them and determine where galaxies can and cannot form. They are not the background of the cosmic story. They are its stage. And in their silence, they preserve something precious. While galaxies and clusters have undergone eons of violent transformation, collisions, mergers, explosions, the voids remain pristine. They are the quiet historians of the universe, still bearing the imprint of the primordial fluctuations that gave birth to everything we see. Their simplicity is their strength. They are untouched by the chaos of starbirth and gravity. In their geometry, we find echoes of the earliest moments of space and time. The voids also offer us a unique window into the unknown. Because they are dominated by dark energy and nearly free from gravitational interference, they allow us to test the very foundations of physics. What is the nature of dark energy? How does the universe expand on the largest scales? Do the rules of general relativity still apply in the most desolate regions of space? In the voids, these questions become clearer. The signals are not muddled by complexity. They emerge through stillness. Perhaps the most profound truth the voids reveal is that meaning can arise from absence. That structure can be born of emptiness. Without the voids, there would be no web, no galaxies, no places for stars to form or for planets to spin. Just as silence gives music its rhythm and empty space gives architecture its shape, the voids give the universe its structure. They are not the negation of matter, but its framework. The darkness between the stars is not a void of knowledge. It is the key to understanding it. So, if we wish to know where we came from and where we are going, if we hope to glimpse the destiny of all things, we must learn to look not just at the light, but at the shadows that surround it. For in those cold, quiet stretches of space, the universe tells its story most honestly, not in bursts of brilliance, but in the graceful, expanding stillness of the void. In the end, it is not the stars, but the silence between them that holds the deepest answers. If you enjoyed this video, please give it a like and subscribe to our channel. Let us know your thoughts in the comments. We'd love to hear from you. Thanks for watching, and we'll see you in the next one.